Hey everyone, we're going to kind of go over some stuff you're going to need to know for the test on. I do a test on Friday and Monday now for this unit on the probability stuff, the probability distributions. I know it's last minute notice, but I'm kind of running out of time for the term, so I wanted to kind of get this wrapped up so we can do one more unit on statistics before the term ends and your class is over. So this is stuff that you need to know for the test. Everything we've already covered. I'm just going to kind of briefly review a lot of the stuff that you definitely are going to need to know based on what we've seen on the study.com stuff and the classes and the lessons that I've given and the work we've done. So probability distributions, like we talked about, are sometimes it's a function. It's a tool we use to track specific outcomes of events happening in the real world. And the probabilities of that event happening. So like what's the probability of, let's say you're getting a snowstorm next Friday. There's a way to actually track that based on weather and all that. We can kind of figure it out. Meteorologists use all sorts of models. What's the probability that we randomly choose a student in the hallway that has green eyes and red hair? There's ways to calculate that. Those are the distributions we're looking at as we've gone through this unit. We've classified our variables as either numerical or categorical. We can work our probabilities on both of those as long as we can actually put the categorical variable into a numerical representation. So like if we're looking for male or female, would make males 0, females 1, or males 1, females 0. If we were looking for like redheaded, green-eyed people, that would be our 0 probability, our 0 number. Everything else would be a 1 because we just need to have a success or a failure number. From that, though, we can break our variables down, our numerical variables down into discrete outcomes and then continuous outcomes. Our discrete outcomes are outcomes that we can actually count. How many people in Carver High School have red hair and green eyes? We can count that number of people. We're not going to have a fractional person. Continuous outcomes are outcomes where the result can be a fraction or it can be some sort of range of answers. We're waiting in line for our coffee between 2 and 3 minutes. It can be anywhere. It could be 2 minutes, it could be 3 minutes, it could be 2 minutes and 15 seconds. Where it's a continuous thing, we're not able to put a specific number on it. The probability distributions for discrete variables, we actually always list in tables or graphs. So you think of flipping a coin, the probability of a head is 0.5, probability of a tail is 0.5. That's my table of the probabilities of flipping a coin. Simple as that. Probability of rolling the different numbers on a dice. You'd list all the numbers out and the probability would be 1/6. Maybe they're a little different. Maybe the first option, maybe there are 3 options and the first probability is 50%, the next 2 are 25 or 50, 30, 20, things like that. The table for the discrete variables would be listed out that way. The continuous outcomes, that's where we're more looking at the area under the curve, the normal distribution that we talked about, which we'll get to again, where we're looking at variables and numbers under a curve because it's a continuous number. We're not able to put dots on our graph. It's what's the probability of waiting. We know you're going to wait between 0 and 5 minutes. Where inside of that is the probability that you're going to fall. So we're able to calculate the area under that curve with the math that we learned. So to work with some of the stuff we were doing with the curve, we know it's called the normal curve. It's the range of, it's identified with your mean, which is the 0 value, is the mean of our observations and our data. And then it has, in this example, z-scores, but it has other ranges out with the data, which is the standard deviation of plus or minus 1 or 2 or 3 standard deviations above or below the mean. So that's where we have here. Remember that half of our data is to the left, half of the data is to the right. And then remember what this graph is actually showing are the rules for the empirical rule. Which stated that about two-thirds of our data, in this instance slightly more, is within one standard deviation above or below the mean. 95% of our data was within two standard deviations above and below the mean. And then almost all of our data is within three standard deviations of the mean. There are still some outliers. It's not a full 100% under the curve. Inside 3 and -3, we go out even further, but you're starting to get into highly unlikely outcomes of what we're looking at. Remember as well, when we're talking about the mean and the different values, we can calculate these z-scores for each and every observation we make in our experiment using this function to then determine where that number falls in our normal curve so that we can calculate the probability of that event actually happening using the tables and the data that we have. So I'm going to walk through an example just to remind you of the process to do that, what we're looking to do. We have this problem. A radar unit is used to measure the speeds of cars on the motorway. They've done all their data and they've determined that the mean speed of the highway is 45 miles per hour with a standard deviation of 6. So we can draw our normal curve with our mean of 45 and then our rho, they call it rho, the Greek letter rho, the standard deviation was 6. So now I can put in other values here where our different amounts can fall. So you can kind of see that I know then too that 68% of the cars are going to go by this radar gun traveling between 39 and 51 miles an hour. What we're looking for is the car that goes, the randomly picked car going more than 60. So we're looking for a probability of our x being greater than 60. So again, when we're talking greater than 60, our z-scores always represent the probabilities for to the left of that score. When we're looking at greater than, we're looking for values to the right of our number. So we'll have to do a little bit of extra math as we go through this. But remember, our formula for our z-score is just z equals our observation minus our mean divided by the standard deviation. So we end up with 15 divided by 6 for our z number, which equals 2.33. Remember that we're able to look at our distribution tables. There are things online you can use or what I passed out in class. And we find where the probability is at that 2.33 z-score value. And we found that the probability for 2.33, let's say, was 0.9901. So again, that's the probability to the left. So what that's telling us is 99% of the cars on this highway are going to be pinged with the radar and they'll be traveling 60 miles per hour or less. We want 60 miles per hour, more than 60 miles per hour. So we actually have to subtract that 0.9901 from 1 to get our value. And we're looking at about 1% for our answer. So 1% of the cars on this motorway at any particular time are traveling more than 60 miles per hour. That's the math that I'm going to expect to be able to do on the test. Now we get into the binomial model, which now we're talking about probabilities of events happening in experiments. We flip a coin 100 times. What's the probability we got 75 heads? We flip a coin 10 times. What's the probability we only got 1 head? We're able to use the binomial model and our binomial formula to actually calculate what those percentages are. What's the percentage of taking a standardized test and scoring higher than the mean average there? So the mean's 500. What's the probability of scoring 575? We can figure those numbers out based on this formula. So to recognize a binomial model, though, you need to kind of have some stuff, some information. We have to have, the outcome has to be a count. So we have to be able to count how many times something happened. We flipped the coin 10 times. what's the probability of getting 4 heads? We're counting for 4 heads. Once you have a count outcome, you're able to count your outcomes, then you have to look for all these other criteria. There has to be a fixed number of trials. We're going to flip a coin 100 times. We're going to flip a coin 1,000 times. We're going to flip a coin 2 times. What's the probability of getting 1 head? Probability of getting no heads. We're trying to figure that out. There can only be 2 possible outcomes. The simplest way to think of it, the 2 outcomes are a success or a failure. We're going to flip a coin 1,000 times. Our success is going to be getting a head. Getting a heads. What's the probability of getting 400 heads? The success would be a head. Flipping a coin, getting George Washington facing up. That would be your success. The failure would be getting the tails. There can be more than one possible outcome that represents a success or a failure, but the only 2 possible outcomes for our experiments are that success and that failure. So think of it, if you're rolling 1 die, you're trying to get a 3. The success is a 3. That's a successful experiment. We rolled the dice, we got a 3. The failures are a 1, 2, a 4, 5, or 6. So there are 5 possible outcomes that actually make up the failure, but it's still 2 possible outcomes. We had a success or we had a failure. The other thing you need to know is that the probability of the success is the same each time. Rolling a dice, it's always going to be 1/6 of a chance we're going to get a 3. There's always a 50-50 chance we're going to get a head when we flip a tail. Flip a coin, sorry. So that the probability does not change, which kind of ties into the last one, that the probabilities, the trials are independent. The 100 times we flipped the coin, each one of those was an independent separate event. The outcome before had nothing to do with the outcome of the present experiment, which had nothing to do with the next 3 coming up. Everything was independent. So hopefully that you remember that, and that makes sense. Finding the binomial probabilities, we're able to use this crazy looking formulas. We're told the number of trials, the number of successes, and the probability of each success in our questions, in what we're looking to do. So we're able to plug all those numbers into our formula and get what the probability is for that specific event. What's the probability of getting 11 heads when we flip a quarter 20 times. Plug all the numbers in, it'll pop out a percentage. And I'll work you through one more problem just so you remember how to do it, so that we can see what that does. What I'm going to do is rolling a dice. We're going to roll 2 dice 20 times. We're going to try to get a total of 7 times. So when we kind of go through what we have, our number of trials is 20. We're going to roll the dice 20 times. The number of successes we're looking for, our X value is 7. We want to get a 7. It's unfortunate that they're the same, but we want to get a 7 times. We want to have 7 successes. And then our probability of getting that 7, if we remember back from the last unit, is 1/6. There are 6 different ways we can get a 7 rolling 2 dice. We can get a 2 on the first dice, a 5 on the second dice. We can get a 5 on the first dice, and 2 on the second dice. 2 completely independent, 2 specific different outcomes. Even though it's a 2 and a 5, there's 2 ways to get it. Same thing with the 1 and a 6, same thing with the 3 and a 4. So there are 6 possible outcomes to get a 7. There are 36 possible outcomes when you roll 2 dice. So 6 over 36 simplifies to 1/6. So now I have the n, the x, and the p that I need to plug into my formula, or my equation. When I look at it, though, I need to figure out that crazy c number, which is the n factorial over n minus x factorial times x factorial. So I have to figure that number out first. So my n factorial is going to be 20 factorial. It's going to be divided by 20 minus 7, the number of trials minus the number of successes, all factorial, times the 7 factorial. When you do that math out, you end up with 77,520 possible combinations of ways, rolling the dice 20 times, we get 7 sevens. So just think of it. We can roll the dice 20 times, we get 7, the first 7 rolls. That's one possible outcome. We get 7 on the last 7 rolls. That's our second possible outcome. We could get 7 on the middle 7 rolls. There's ways to calculate it. The formula that we had there calculated 77,520 possible times. So that's the first term in our binomial function equation, 77,520. Our next thing is the probability of a success raised to the number of successes. So the probability of a success was 1/6. We're raising that to the 7th power because we're looking for 7 successes. Then that's multiplied by the probability of a failure, which was just 1 minus the probability of a success, or in our instance 5/6, raised to the 13th power because that's the number of failures. When you plug that math into your calculator or the computer that you're using or whatever you're doing to calculate these numbers out, you find that the probability works out to be 0.02588 and kind of goes on forever. We're going to cut it off, and I'm going to say that there's a 2.59% chance that if we roll dice 20 times, we're going to get 7 sevens. Does everybody remember how to do that? That makes sense to everybody. We're kind of familiar with that. We're comfortable with doing that math because this is what you're going to need to be doing on the test. I'm going to put out a packet tonight on Google, or today on Google Classroom. If you want to start working on it at home, it's the review packet that you'll be working on in class on Thursday as well. We'll go over it on Thursday in class, and then, like I said, the test is going to be for Cohort B, written part on Friday, online part on Monday. Cohort A, it's online part on Friday, written part on Monday. So definitely start looking through the stuff. Try to remember what's going on. Try to get ready for this test. Try to finish up this term strong with a good grade. I am in the process of entering the grades for that last test we took. I finalized how I'm doing that, so I'll get those grades in. Everybody will see what they did there. I will say that the lowest grade on that test is going to end up being a 70. You may not have actually scored a 70, but that's what the lowest grade will end up being for the class, and then it'll work its way up from there. So hopefully I can get those in probably tomorrow as well. So I'll talk to everybody tomorrow on the half day, and then I will see you on Thursday.